I spent the past week with my head down trying to figure out exactly how I wanted to design the barrel modules for my coil gun project. The barrel modules are the modular slices of the barrel that will be the most energy intensive components of the entire project. It's a pretty important part because if this thing ends up exploding, it's probably going to be due to a barrel module failing. And in the previous video I talked about my theories on how one could achieve a high efficiency coil gun by having really thin barrel modules. And this has made the design a little bit more complicated than it would be otherwise. But before we get into the actual design, let's talk about some of the initial design parameters. I started out this week doing a lot of math to try and model the path of the projectile. I quickly realized though that I was being too optimistic with my calculations, that I would never really get to that point, or at least I wasn't willing to spend the money to be able to get to that point. You may remember that in, I think a couple videos back, I explained my belief that capacitors were inherently inefficient in a coil gun system and could not allow for high efficiencies, and thus a direct drive system was the only way to achieve higher efficiencies. What I mean by that is that the coils would be directly connected to the battery. The battery would be directly powering them, and you don't have a secondary buffer like a capacitor bank that would be powering them indirectly. And in doing my calculations, I realized that the battery itself would be the primary bottleneck in a system like this. In order to achieve muzzle energies of around 1,000 joules, which is a very respectable gun muzzle energy, with a reasonably short barrel length, you would have to have a battery that can output 3 to 6 millisecond pulses of around half a megawatt, 500,000 watts, which is, that's a lot. I don't have the money for a half a megawatt battery, so instead of trying to get to that point, I instead went off of what I could get for a reasonable price, and again, as I stated in the previous video, went for efficiency and not power. Battery hookup, which is the absolute best place to get lithium-ion batteries for extremely reasonable prices, currently has these pouch cell batteries. They're the SPIM 08HP. They're really decently sized batteries. They're standard lithium ion, so they are a nominal voltage of 3.7 volts. Capacity of 8 amp hours, which is pretty good. But what is most important to me is that they have a continuous discharge rate of 200 amps and a 3-second pulse rate of 400 amps. I've seen short circuit discharge tests with these batteries, and in those tests they overloaded a 600 amp clamp meter. So I know that these batteries can discharge at least 600 amps, and according to the battery hookup website, they have an internal resistance of less than or equal to 0.8 milliohms. That's 800 microohms, which is extremely low, which will be really good when trying to get an efficient discharge at such a high amperage. So knowing that these batteries can output an appropriate voltage, I went from there. I think that I can get 600 amps out of a battery pretty reliably, pretty safely, without blowing anything up. And then the reason I think I can do this is because the coil, the entire barrel, is only going to be on for 3 to 6 milliseconds. It's an extremely short duration. It's so short that data sheets don't really show that kind of low single use case scenario very often. So for some of these components, I kind of just have to approximate what I think it'll be at for those really short durations. But either way, I know this can do 600 amps. So for the battery, I'm thinking I would get 16 cells and arrange them in 8S2P configuration. So to parallel, that would allow for 1200 amps output over that 3 to 6 milliseconds. And then 8 series, if they're fully charged up to 4.2 volts, that would be 33.6 volts. So 1200 amps at 33.6 volts, that's 40,320 watts, 40 kilowatts, which is very respectable. It's not enough to be insanely powerful by any means, but it is certainly respectable. So once I got to this point, figuring out what I wanted to do for the battery and what my capabilities would be, I kind of ignored the calculations for a little while and instead went to the design, knowing that the calculations wouldn't be entirely representative of what I could achieve. So I'll show you what I've designed. So So we'll start out with the circuit board. Every barrel module has its own circuit board, and the primary component on that circuit board is this really big MOSFET. This MOSFET is the TO-247 package. The main reason I wanted to use that one is, well, of course it can do a lot of current, but more importantly, the leads are spaced out so I can get proper wire connections, proper traces in there. And this circuit board was designed in Eagle. Eagle has a very handy feature where it automatically links to Fusion 360, so I'll just be showing it to you in Fusion. So of course this is the MOSFET on top, and then if I turn it over, you'll see some SMD components. Over here, there's a PNP, NPN transistor in the SOT23 package, and then a couple of 0805 10 kilo ohm resistors. These 5 components are what drive the MOSFET. They essentially take a very small current at a small voltage from your microcontroller, say an Arduino or something like that. At this hole right here, this is where a signal pin would be, but they take that small current at small voltage and then increase it to the full voltage at a higher current to fully turn on the MOSFET. So effectively what they're doing is they're giving the MOSFET logic level control. So every circuit board, every barrel module has that logic level control built into it. So all I have to do is wire it up directly to my microcontroller and say turn on, and it'll turn on. Then over here, these big wide flat SMD components here, these are diodes. These 2 diodes are in parallel and they're running in the opposite direction of the current across the coil. So they are flyback diodes. So when the coil turns on, it pulls a projectile through, but then when it turns off, the opposite current is generated in the coil, which could potentially be damaging to the MOSFET or the battery or other components. So these flyback diodes allow that current to dissipate by being in the opposite direction. And each of these is rated for 250 amps over an 8.3 millisecond period. Oh, I should also mention that each of the modules needs to be able to handle and conduct 300 amps. The idea is that there will be 4 of these modules on at the same time, so 1200 amps total. That's the maximum the battery should be able to output. So then each of the 4 only needs to be able to handle 300 amps, which is much more reasonable. Still a lot, but more reasonable. I typically get my electronics from LCSC.com, which is a sister company to JLC PCB. And since they are a Chinese distributor, they do have a lot of Asian brands. So these 2 components, these 2 bigger components, the big MOSFET and the flyback diodes, they are both Chinese manufacturers, which makes me a little bit uncomfortable just because I've had experiences in the past where the components were not rated for what they claim to be rated for, but LCSC is a reputable distributor, and as far as I know at least, and they both have comprehensive data sheets that are in English that have everything that I would need. So they seem legit. I'm just going to assume that they're legit. I think anything that comes from LCSC is probably tested and ensured of quality. And these components are rated for a lot more than I'm going to be pumping through them. These MOSFETs are rated for a pulse current of up to 800 amps. And again, I'm only doing 300 amps per module. So there's a lot of room to expand there. And then these guys are again rated for 250 amps, but I have 2 of them in parallel, so it's more like 500 amps. And all of these components are also rated for up to 80 volts. And I'm only running 33.6, so I could double the battery voltage, thus quadrupling the wattage, and everything would still be able to handle it. On the component side, I'm definitely going a little bit safe. If the MOSFET fails, MOSFETs typically fail on, which would mean that it would just be continually discharging the full current of the battery through it, which would probably blow up the battery, which is not something that I want to do. Back to the circuit board here. So you've got your components on the bottom side and then the big MOSFET on top, and then you have some really traces here, or at least as big of traces as I could make it. I made it so that the traces are on the top and bottom layers. So I'm effectively doubling the trace width by having it on top and bottom. The traces are still not as thick as I would like them to be, but I'm not too worried about it. The bottleneck, as far as current goes, is not in the PCB, I don't think. I'll show you that in this. I'll show you where I do think it is in a second. The other reason I'm comfortable with these PCB traces is that they're super flat. Pretty much the entirety of it is exposed to air, which means that it can dissipate that heat off quite a bit, and they're really just big heat sinks. And there's also going to be quite a bit of aluminum around here to soak up that thermal energy, so I don't think it's going to be too big of an issue. I definitely don't think the circuit boards are going to explode. Other things are going to explode before that happens. So this is the circuit board. This is the first thing that I started designing, and that brings us to the actual barrel module design. This is the barrel module, or at least how it's looking so far. So right here is the PCB, as you saw, and then the whole thing is up against this plate. This is the backing plate. This is what everything sits up against, and it's also what will be squishing all of the barrel modules together. This is a 1.6 millimeter aluminum plate, and it's kind of the foundation for the entire module. So this backing plate has two holes here and here that line up with the holes on the circuit board. So this is where the circuit board mounts. It'll just screw down to here. Then you also notice that down here, the aluminum is a little bit thicker. I designed a little aluminum plate that will attach down there, down here, and this is where the majority of the surface area of the MOSFET will be pressing up against. And then this plate also has holes in it for the mounting screws of the MOSFET to go through. So this is the primary heatsink. It's a good chunk. It's 3.2 millimeters thick of aluminum that should be a decent heatsink. Then this other plate is also 1.6 millimeters. The reason I made it 1.6 millimeters specifically is because that's how thick the circuit board is. The MOSFET is partially on top of the circuit board, and then this way everything will line up nicely. Everything will be flush with the 1.6 millimeter aluminum plate. Then of course up here is the coil. There's nothing really attaching it. Not really gonna worry about that. Once you get multiple barrel modules, the coil should be squished into place, and it should be a pretty tight fit around the 10 millimeter carbon fiber tube that I'm gonna have as the actual barrel. Oh yeah, and I didn't show you the back of this. The back of this looks really cool. All of the SMD components here have a little cutout in the aluminum plate. That's where they go. So I was kind of constrained for space here because I know they needed to fit in this little cutout. So all of your components are back here, and they're distanced from the aluminum so they don't short to it. But yeah, it all fits in there really nicely, and I'm very happy with how it looks. You might have also noticed that the backing plate has this slit in here from the electronics hole to the barrel hole. That is for the leads, the wires of the coil. Once you have a bunch of these that are squished together, you won't have room to take the leads of the wires and just move them anywhere to stick them into the circuit board. By the way, these holes here, that one and that one, are where the leads of the coil go. But you can't just stick them anywhere willy-nilly because there won't be room for it, because everything's going to be really tight in here. So you'll have one lead that'll be coming out of here and then one out of the bottom here, because that's just where you start and stop winding the coil. So then they can both go down through this slit without taking up any room because they will be flush with the aluminum plate. But this coil took me a bit of thought to figure out, specifically the sizing, the gauge of the wire, all of that. But I came up with what I think is a pretty clever solution. What I did is I created a simple program in Java to figure out all of these parameters for me so that I don't have to. So I give it a few parameters up here. I tell it what the wire diameter is based off of the gauge of the wire. This should be 19 gauge. I then tell it the length of the coil, that's the thickness that I'm allowing for the coil. I then tell it the wire resistance in ohms per meter, and then the ideal resistance, which is the total resistance that I want the coil to be. Then I give it the barrel diameter. That's the diameter of the carbon fiber tube. And then it gives me this data. It digitally winds the coil and then gives you parameters based off of what you told it the conditions of the wire is. So given these conditions, these constraints, and trying to get to a coil with a total resistance of 96.2 milliohms, the program realizes that I could make a coil with 63 turns, 9 layers, 7 turns per layer, and the total wire length would be 3.64 meters. Then down here it gives you some data based off of if you didn't have the last layer, because a lot of times when your numbers don't work out quite so well, you'll have 1 or 2 or 3 turns on that last layer, which you don't really want. That's not uniform, it's not great. So then it gives you some data on if you didn't have that last layer to make things convenient for you. So all I did is I wrote this program, I verified that it worked, and then I just started plugging in numbers, specifically plugging in different wire gauges. I started with 16 gauge wire, which is what I currently have, and the diameter of the coil ended up being way too large. I then went to 18 gauge and the diameter was really small, but the wire itself was really thin and I didn't think that could handle it. I went up to 20 gauge and it was a little bit too big, bigger than what I wanted it to be. And then I discovered that 19 gauge wire is a thing, or at least I can get it from a single Amazon distributor, but that's it. But 19 gauge wire ended up being pretty good. Right in the middle, it ended up being what I wanted it to be. So at that resistance, the coil is a good diameter that will fit into my module nicely at 27 millimeters. So I went with that. That's my wire gauge, 19 gauge. And yeah, that's how I figured out my wire diameter, is based off of this. Oh, and the total resistance. That is in order to achieve my 1200 amps, or specifically my 300 amps per module. So this 96 milliohms, when you add in the resistance from the MOSFET and resistance from the internal resistance of the battery, you end up getting around 1200 amps. And it's also not taking into account the resistance of the bus bars and other connecting wires. So in reality, it'll probably be a little bit less than 1200 amps, which is good. I mean, playing it on the safe side is not going to hurt anybody here. But yeah, so that 96 milliohms is in order to get 300 amps per coil. And then I brought up the bottleneck, the current bottleneck earlier. That is, I think that's a coil, because these things, they're 0.94 millimeters in diameter, and they're all bunched together. I think if anything is going to fail, it's going to be the enamel copper wire in the coil. And of all places for it to fail, I think it's a good place, because if the components fail, if the electronic components fail, they're probably going to fail on, and then we'll have an inrush current that'll just kill everything. But if this fails, it'll effectively be like a fuse. It'll break and then you'll have no more connection and then nothing will happen. So I think this is a good place to fail. I am okay with the coil breaking, but I would not be very encouraged if the MOSFET failed. So this is the barrel module. Now let's talk a little bit about how the barrel modules are actually all going to come together to make the actual barrel. So this is my design for the barrel so far. I have the 10 millimeter diameter carbon fiber tube at the center. By the way, that's 8 millimeters internal diameter. I intend for the projectile to be 7.5 millimeters in diameter and around 50 millimeters long, just a soft steel. But the backing plates for all these barrel modules have a lot of holes in them, and you want to stack them all butt to butt, face to face. So my thought for this is that you'll just have a bunch of a bunch of threaded rod that you'll run some lock nuts down, and then use that to clamp everything together. I think it should work pretty well. I could make it stronger if it's not, but I think it'll at least work for preliminary tests. So I currently have 7 thread rods going through here, which is kind of overkill. but it's what I could do. It's kind of just the only thing I was able to do, because I needed some up here to clamp on the coil. I needed at least two to hold the circuit board in place. I needed one to go through all of the MOSFETs. Then I needed two in the corners to hold the bus bars. I haven't modeled the bus bars yet, but what I'm thinking right now is that the bus bars will hang below it, and that they will be held in place by 3D printed brackets that will hang from these two threaded rods here. And then sticking on the topic of the bus bars, the power distribution, I didn't bring up these pads on the front of the circuit boards. That's the power distribution solution. So the bus bars will be on the bottom, and then I think I'll just have a bunch of short, maybe 14 gauge wires with wire lugs that'll screw into the bus bars, and then I will remove the insulation from the end of the wire, and I'm just going to solder them directly onto these pads, which seems kind of like a crude solution, but I think it'll work. I don't think it'll hurt me, especially since these pads have really big traces around them, so they're kind of like heat sinks. I think it should be fine. I don't think it's necessarily going to be a bottleneck, or at least not more of a bottleneck than the actual coil wire is. So then the idea for keeping these all together is I'll put one on, and you fix it in place with some screws, and then you just slide the next one on, and you put some more screws on it, and then you really tighten them down to press them up against each other. The depth of each of these coils is just at 8.2 millimeters. They're 8.2 millimeters thick, and things line up pretty darn well here because the MOSFETs are end to end. They are being pressed up against. So what this means is that the MOSFET, or at least the end of the MOSFET, has a chunk of aluminum being pressed up against its front and back, and like really clamped on there. So I'm very happy with that. I think that should be a pretty good thermal transfer. And then the backing also happens to line up really nicely with the edge of the coil. So not only will it be clamping onto the MOSFETs, but it'll also be clamping onto the coil, keeping it in place, which is why I'm not too worried about fixing the coil to the backing plate, because it's going to be clamped on by the next backing plate. So yeah, that is the design for the barrel thus far. Of course, I only have 5 modules here. I'm thinking it'll be 25 to 28 modules. This whole thing is 300 millimeters long, which is actually longer than I can get this threaded rod. This is M3 threaded rod, and I can really only get it at 250 millimeters, so I'll have to try and source some longer rods for that, but whatever. So this is the barrel module design. I'm happy with it. It looks really nice, and it's very compact. I originally was thinking that the barrels would be 10 millimeters deep, but they're 8.2, so they're even less, which is spectacular. Which again is what I want. I want them to be as thin as possible. I think this can handle the current, at least for the 1 millisecond that each barrel will have to, or each module will have to endure it. It's where the whole thing is like 3 to 6 milliseconds. Each one's only going to need 1 millisecond, maybe 2 milliseconds. So not too worried about that. I'm not too worried about that. I'm still kind of worried about it. But anyways, there are a couple of unknowns with this design. The bus bars aren't really an unknown. I'm pretty confident I know what I'm going to do for that. But for the actual barrel module, there's 2 things that have to do with an electrical connection that I'm not sure about. These pads on the sides here, they both have 6 vias in them. So that's little holes in the circuit boards that go all the way through, which means that there could be an electrical connection on the bottom of the circuit board, which is being pressed up against the aluminum frame. So I don't know if those are actually going to make sufficient electrical connection. If they do, I'm going to have some barrier, some thin barrier in between the circuit board and the backing plate, the aluminum backing plate. Otherwise, you're going to be shorting your ground, your source voltage, which is not a good thing. But I think it could
if it is a problem at all, I think it could just be like a sheet of paper. Um, Hopefully, it doesn't have to be too much more than that. I don't think it should be too much of an issue. The other thing, which could be a little bit more interesting, is that the back of this MOSFET is an exposed metal heatsink. And oftentimes with these big MOSFETs, the heatsink is connected to the gate of the MOSFET. So if you just clamp it directly to a heatsink like this, if you were to run current to the heatsink, the MOSFET would turn on, or at least it would try to turn on. What that also means is that if all of these heat sinks were connected, which they probably would be, if you turn on one of the MOSFETs, then all of them would turn on. But I don't know if that heatsink is actually electrically connected to any of the pins. The datasheet does not explicitly say that it is, so I don't know if it is or not. I'll have to test that once I actually get the components. There's not really any way of me to know now, but if I do, then I'm probably going to have to add in some padding below here. I can get these small 0.3 millimeter silicone pads, which would go in between there. So those silicone pads have high thermal conductivity, but of course extremely low electrical conductivity. So they would separate it electrically, but still couple it thermally. So if I did have to do that, I would be increasing the thickness of this whole barrel by 0.3 millimeters, which is not a big issue. It would come up to 8.5 millimeters. It would allow for a little bit more room, a little more wiggle room for the coil, which is not ideal, but it is what it is. If I have to do it, I have to do it. But yeah, this is what I've been spending the last week trying to figure out, and I'm happy with it. It looks good, and I feel like I've gone through every failure method, and if it does fail, I will know where to look. And I mean, just look at it. The thing looks really cool. It looks like some mad scientist experiment, something. I don't know. I'm happy with it. And about that math that I started out doing, the first step in this process, it wasn't entirely useless. It was actually pretty interesting. So I just did some very simple calculus, assuming that the projectile would accelerate constantly throughout the barrel, which again is my goal for this project. So then with that simple calculus, in addition to the kinetic energy equation and the equation for wattage, I was able to calculate, or at least make a simplified equation that would calculate the amount of energy I use based off of the input velocity, based off of like an x value velocity. And this equation already takes into account the 40 kilowatts that I'm inputting and the 250 millimeter barrel length or acceleration length. I was then able to simplify the kinetic energy equation by just inputting the math and then divide them, the kinetic energy over the used energy, to calculate my efficiency. And I came up with this equation, 0.009 V cubed over 20,160. So if you model that on a graph, you get, well, it's an x cubed graph, so it starts out low and then flattens out at 0 and then keeps on going really high. And I'll put a picture of that graph on the screen here. So on this graph, the x input is velocity, that's the velocity of the projectile, and the y value is the efficiency. So I have a horizontal line at 1, which is 100% efficient. Anything beyond that point where these two graphs meet, beyond the 100% efficient, is just not realistic. Of course, you can't go beyond 100% efficiency. Anything beyond that would actually reduce the efficiency because you can't accelerate the projectile that quickly. But what this tells me is that, well, first of all, the whole thing is positive, which means that the faster I go until I reach that point, the more efficient it gets, which is good. This also tells me at what point exactly the system is most efficient. So where this graph reaches 1, where it reaches 100% efficient, is at around 130.8 meters per second velocity. What this means is that given these parameters, given the battery wattage and the length of the coil and everything else,
if I were to get the projectile up to 130.8 meters per second, the system would be 100% efficient, which is of course unreasonable, but at least I know I have a frame of reference. That's my goal. That's where I'm trying to get to. That's where I'm trying to approach. So what that means for my ideal projectile properties, my mass that I'm going for is 18 grams. That's pretty arbitrary. That's just based off of the size of the projectile and the density of steel. That doesn't really matter necessarily. Then the length is 50 millimeters, as I said earlier. So the muzzle velocity, the ideal muzzle velocity at 100% efficiency is 130.8 meters per second. And then plugging the muzzle velocity and the mass into the kinetic energy equation, you get 154 joules. So if this system reached 100% efficiency, I would get 154 joules of kinetic energy out of it. So I know what my goal is. I know what I'm aiming for. So there you have it. That is my progress on the coil gun project. It's been a week of heavy thinking, and honestly there's not a ton to show for it, but I'm very happy with what I've been able to produce. It looks good. I think it might just work, which is crazy. If you would like access to these files, access to the circuit board files or the CAD files, or even the program that I wrote to calculate the properties of the coils, you can gain access to those via my Patreon. All the project files will be available on there, and as the project moves forward, as I develop the rest of the system, those files will also be available on Patreon. If you would like more frequent updates than my occasional video on YouTube, you can follow me on Instagram. So now that I've designed everything, I need to go spend like $200 to $250 on electronic components and materials and batteries and everything, which is gonna hurt a little bit, but you gotta do what you gotta do. It's for science, so it's always worth it. So you can get access to my files on Patreon, link in the description. That's all I have for now. Bye.